information will actually be on the project webpage. You can see it on the slide. And we also have a wiki page that we're starting to populate. And here a lot of the details are going to be available. Ashok, can I ask you to go to slide number 5? And at this stage, I would like to call for active participation from everyone. So ways to get engaged and get started will be, we have already a Slack page that I will ask to maybe join. And we have a number of mailing lists, and these mailing lists for all the interested parties, following these links, you will be able to join these mailing lists so that you are in the know of what is really happening. So we have a developer-specific mailing list, a general discussion mailing list, and another mailing list for the announcements. All these links are also available in the wiki page. So just by going and clicking on the relevant mailing lists you want to subscribe to, you can get started. Once again, I'm very, very excited to actually kick off this project, and I can't really thank enough Intel and Sprint for this tremendous seed code to get this very important project going. And with that, I will let Ashok take over.
So, Nath, yep, you go.
Yeah, all right. Okay, thanks, Rose. So starting with the slide, basically, this slide will try to cover the high level or the top level description of the project. Basically, this project, you can think about the collection of around 13 VNFs. The VNFs are highlighted and marked in bold, starting with MME, HSS, DB, S Gateway C, S Gateway U, P Gateway C, P Gateway U, and there are some CDF, CTF, and SGX components. These 13 VNFs, when you look at the repo structure, they are packaged in the 7 repos that we have in the OMEC GitHub project, and you will find various components in the repos. So for now, these 13 VNFs are actually spread out in 3 repos, which is the OpenMME repo, the NGICRTC repo, and the C3PO repo. And there are other repos. For example, there's a traffic gen repo. There's some deployment and scripting tools as well in the repo. So what does it include? Basically, this project with all its components, it has gone through extensive software lifecycle and secure development lifecycle process at Intel. That means it has gone through at least the standard lifecycle processes that followed in the industry. Plus, there are specific guidelines and processes that Intel follows separately. It also includes the scans. That means each and every line of the project, that means each and every line of source code has gone through project scans, which prevents us from making any code contamination and cause any license conflicts. So that's number one. Then with these components, we basically have a complete connectivity. That means we have tested each and every component with each other, working hand in hand. It has secure billing and charging, charge data handling capabilities, which we'll talk about more in detail. Then we have we say we have components there that are compatible and features that are compatible with 3GPP release 13. However, you can see there is a star mark there. Although we claim, but there it's still a reference project. We want to make it very clear. It's a reference project. It's evolving, and it does have some features, but it also has some features that are not there. There are limitations which we have tried to clearly articulate in the readmes and the release notes. So would encourage everyone, whoever looks at the code, to look at the readme and the release notes first and set the expectations accordingly. Okay, so then the way we have designed this components is basically think about it as like Lego building blocks. So we have building blocks through which you can create a lot of different variety of, basically you can create your own as long as you are within the guidelines. You can customize the solution as much as possible. So that's why we call it, it's like a lightweight solution. The reason we've done it is that we try to make sure we can cater to different type of deployments, including IoT applications. So some of the components may not be needed. Some components may be configured in a different way. So we have tried to address those as much as possible. And last but not the least, we have continuous integration, continuous deployment integrated, and the set of project and the set of components support all these tools. That means these components can be tested, can be built, tested, as well as can be integrated in any Jenkins-like environment. All right, so then we have the link for you. We can go to the next slide. All right. So this is what the stack looks like. Basically, these are the 13 VNFs here. This is the stack. I'll not go through the components individually here, but what we call this, whatever we are looking at, this particular stack with all these instances, this is what we call as a one frame of capacity. Basically, the idea is this frame of capacity has a certain parameters, certain test parameters, certain performance parameters that we have tested it against. However, if we want to scale and we want to support various kind of deployments, the idea is we will replicate or scale these frames of capacities. So that means if you need more performance, you will basically add more frames of capacities. And the stack that we are looking at is just one frame of capacity. However, these components, they have some features that I want to extensively talk about on this slide. For example, if you look at the green boxes, those green boxes are basically SGX-based billing and charge data handling systems. The reason for this is the charge data and the billing data, they're very sensitive data, and we want to make sure that we can protect the data, we can provide the confidentiality, the integrity, as well as we can make it fully auditable. So Intel SGX is a feature that's available on Intel CPUs that can give us those properties. So we use Intel SGX for protecting the billing and charging data. And we also have tools and features that we can use in this stack for if you want to basically run it in a virtualized environment, or you want to containerize it and orchestrate the way you want. Again, I want to be very clear here. There may be features. Sorry guys, can we unmute?
Can you mute? Yeah.
Okay. So there may be features which are there but may not have been completely tested. There may be features which are missing. Again, those are we try to document those as much as possible in the release notes. Okay. So with that, I want to hand over to Ashok. We'll talk about in detail about the performance and functionalities. Ashok.
Yeah. Nice. Thanks. So my colleague Somnath has said, so let's do it a little more, and then I'm going to start taking this thing apart, at least on this slide, and then we'll go into a demo. So essentially, functionality-wise, as you packet processing. So there's a pass to this code, and we have so pass to this code was about a year back. I know many.
Ashok, we can barely hear you. Could you speak up?
Sorry, can you hear me? Hello?
Much better.
Okay, fine. Sorry, I think I was speaking to myself more than the audience. Sorry about that. So basically, the S&P gateway part. So going through these bullets, what we have is we have a pretty high performance data path. When I say pretty high performance, the numbers are there. We basically have 4 cores, and we can handle about 2.5 million packets per second. The exact number is somewhere between 2 and 2.7 million packets per second, depending upon the ARP flux you have on the data path. Okay. And you have basically 4 cores that handle that kind of load. Okay. Now we can't anyone in this group in the community today, based on the repos we have open sourced, can actually take this OMEC and test drive it and reproduce these numbers. So we also have open sourced the traffic generator. Okay, so we have our own internal traffic generator based on DPDK's packet gen, which we overlaid for dumping number of flows, GTPU packets, etc. The code itself is instrumented, so we can remove dependence on an S11 interface. So it's got an S11 simulator. So everything is built in. So if community members want to take this and simply push the pedal to the metal and see how fast, how much they can push, everything is built in. The question comes in terms of now conformance. So my colleague Somnath stated multiple times, and I basically want to reiterate that. Wherever you see asterisks, we have done extensive regression testing, and I will go through the chart in the bottom in a minute. But the main takeaway is we can't claim to any degree of maturity conformance. So thanks to many folks on this call today and outside of this call in the operator community, people have pitched in who have taught even leading up to the release a few days back. We had dozens of conformance issues. And I want the community to be very acutely aware of that. We have done our best to capture these issues in the release notes. These issues are not like they're not things that you'll take months to resolve. They're basically fixes that need to happen. Solutions are straightforward. The main problem is the regression spins that we will go through. So we have a path. So it's a pretty simple, very neatly written, the code is amenable. Like Somnath said, they are Lego bricks. You can expand the Lego bricks. You can build in the functionality, the conformance pieces that have been missed, but that's where we are. The other piece on, so Somnath, why don't you cover exactly what SGX E3 does? Then I want to break apart this S&P gateway U thingy, and I want to go into the regression test we've gone through with this.
Oh, sure, absolutely. So basically, the SGX system, as if you remember the stack, it's in this release, the SGX systems are used for handling billing and charge data processing. The reason we use SGX is because of the capabilities that it can provide that can satisfy the confidentiality, integrity, and the auditability of the charge data records. Although we have shown one SGX billing system in one frame, in our labs, we have actually tested up to 7 frames pumping data records, charge data records into one SGX billing system. So the SGX billing system can handle more than 1 frame, but for the sake of simplicity, we have put it as part of 1 frame, but it can handle up to 7. In fact, it can handle up to 11, but for sake of, to keep some buffers, we have put 7 here. Now, one more thing I want to highlight about SGX before I hand over back to Ashok is these systems are Xeon E3 systems. They are 4-core systems, and the SGX components are not running in virtual machines. They are running as processes on bare metal machines. So that's the whole part. They offer full attestation between the components. That means any SGX component can challenge another SGX component, and it can exchange keys after the trust is established. So all those processes are in place. Some of these building blocks for SGX itself is provided by the SGX SDK that's hosted in the Intel website. So I would also encourage people to look at the Intel SGX details and let us know if you have any questions. We can address it in a future session.
Thanks, Somnath. So I'm going to start. Let's start breaking apart this bullet. This S gateway U, P gateway U, Linux, etc. We will. I mean, this is just the first session. I'm hoping we have a few more follow-on sessions where I want to basically sensitize to the community, take the community to the code, the release, the issue list captures it all. But point is this: we have tested. So this architecture is cups. So you have control and user plane separated. So you have a horizontal line of separation between the C and the P, between the C and the U. You also have a vertical line of separation between the S and the P. Okay. Now, essentially, for regression testing, it's a nightmare. We have tested, and thanks to Sprint here, Lyle specifically and his team, we have a level of conformance, basically looking at P caps that have happened between the S and the P. So S5 S8C and S5 S8U. However, over the last few weeks, we have unraveled. Some of it has been fixed. Some of it, so the point is, at this point, I don't know what I don't know or what I don't see. And that's the big caveat. So the tides, so S5 S8C tides, S5 S8U tides, transmissivity of the S11F tide, the associativity is maintained. I'm not sure if I'm making sense. I'm really deep into the code at this point. My point here is each S5 S8 C and U F tides need to have a tight 1-to-1 associativity to the S11F tide. That is so that there is consistency there. I know that from the code. I know that from the regression testing we have done. What I do not know today is some gotchas. Hey, you're propagating the S11F tide into the S5 S8 CF tide. Oh, yes, I didn't know that. So things like this, it's easy to correct, but we need the community to help. When I say it's easy to correct, it's really simple fixes. Okay, fine, don't transmit the S11F tide through, use a separate tide generators, tide seed. Those are simple stuff, but these are things I didn't see this, I didn't catch this, and the beautiful part is the emulators we use for testing do not catch it. So these gotchas were out of real networks, and thanks to many of my operator friends. Okay. Similarly, Linux aware and operable. Big. The fact that it is there is again thanks to my operator friends. So these are DPDK interfaces, but they're completely visible on Linux. You can run Linux commands off these interfaces, the fastpath interfaces. But the point is, how Linux aware are these things? So if I do a ping against the S1U interface, does it happen? Hey, if I send an, if the UE is doing a ping to Google, so if the UE does ping 8.8.8.8, Ashok, does it work? Answer it was breaking as of 48 hours back. So the point I'm making, guys, is the stuff is good, but it needs a ton of your help to get to a point of maturity. It's not product. It's not too far away from getting to be a product, but it needs your expertise to make it conformant. It's straightforward stuff. At the pace at which we work this project, I don't see it taking more than a quarter to make it near product grade, but it needs a huge amount of your pointing out, look at this, look at that, fixes are straight. I'm going to quickly close on the regression matrix that I put in the bottom here. So there are two lines. I have, I think, 1 more minute I have to close. So my point is this: we have 3 different setups here at Intel Labs. The stuff in between. So one is with NG40. So all of these are emulators with different capabilities. The one in the middle with Polaris is the one which is the back end for CI/CD. Okay. Now with the Polaris system, which is with CI/CD, I'm not going to go through each of these yeses and nos. What you guys need to see is everything on the right turns out to be a green yes, and you don't have to take my word for it. The systems are accessible. You can run the tests, and you can come to your own conclusion if it's a yes or a no. More importantly, you guys will come to a conclusion, hey, dude, this is broken. You may be putting a yes there. This is broken. Look at your TIDE. Look at your Linux. And those are the things where I really need, we the developers in this group really need guidance. Okay, the fixes are straight. So let's go through the generators we have. We have put things through, put this system under test through, and we have tested across 3 different vectors. One is the options the code has. So here, the code itself has built-in options to test itself in simulation mode. So you can kick the MME off, you can kick a whole bunch of things off and just test the data path. You can just test the control path. Code has many options. So first is, then you can remove the Linux off. You can just say, hey, I can statically set the ARP table, stuff like that, which is a developer's paradise, to essentially rip things off, cut things off, and just test bare bones. That's one area of one vector of regression. The other vector of regression is the options that exist for the C and U plane separation. Okay, so there is a UDP option which more or less will get deprecated as we go forward. This code doesn't have SXA between C and U plane. Hopefully it will get SXA at some point in time. For now, session information that needs to go from the C to the U is over 0MQ TCP push pull, and the beauty is it has been tested across a few thousand miles. Okay, so which means I put the C a few thousand miles away from the U, and I basically am able to transact S11 messages at a few hundred messages per second for a 250,000 device volume. Okay. The third vector I have is the interface itself. So with Polaris, I have a full S1 MME test, so which means my interface boundaries are S1 MME, S1U, SGI. With NG40, it is S11. With our own traffic generator, it is essentially your programming the switch or programming the user plane, and you're pumping traffic through it. So three tests. With the NG40, we test against the S11. So it's just the C and the U plane that is being tested. MME is part of the emulator. With the Polaris, it's a full spread, which means you bring the S1 MME in. Once you bring the S1 MME in, you're bringing the MME, the HSS, the database, the charging functions. All of that gets tested. Okay, and then you have the option of just testing pumping traffic. You can see on the far left here performance. So we have basically set it to these performance numbers. This is what we have measured. So with the NG40, we have measured what you see here, 50,000 devices that are transacting on the S11 at 1,000 transactions per second, doing about 0.9 million packets per second. With Polaris, we bring that number down, primarily the 250 transactions per second. I'm not going to say how high we can go. I'm basically going to say what we are stable at. So which means that if I run 5 tests, I'm going to be able to reproduce these same numbers every single time. That's what we have done. Okay, so 250 transactions per second, less than 10,000 packets per second. And with our own traffic generator, we have pumped as high as 2 million packets per second. Okay. With that, I'm going to stop and let's go and take this thing for a drive. Somnath?
Yeah, sure. Okay, thanks, Ashok. All right. So initially, I was leaning towards the video of the demo, but my team here encouraged me a lot to do a live. So I'm going live. A live demo on the real setup. So let me share my screen quickly. All right, let me know if you're able to see my screen. Loading. Okay. Yes. All right, so hopefully it has it's loaded. So, okay, cool. So here we have split all the 13 VNFs that we talked about. We grouped them, and for the sake of this demo, we have grouped them in 3 screens. So basically, starting with this screen that you're looking at, this is the charging and data and billing data handling screen, where you have the SGX KMS, the dealers, the CTF and CTF, the charge trigger function and the data functions, and the router here. Again, a point to note here is look at the folder names. The folder names will tell you exactly which component it is and what is being run in that. So this is one screen. The other screen here is again split into 3, starting with the load tester, which is the Polaris load tester on the top, the CP and the DP, the control plane on the data plane, the left hand side and the right hand side respectively. And we have the MME and the HSS in another screen. So you can see the HSS, the MME, and all the handlers on those interfaces, the 6A, S1A, and the S11 pins on the screen. So starting with the KMS, for the demo, we'll start the KMS. KMS is basically SGX-based key manager, key store. It generates the keys inside the SGX environment so that it cannot be tampered with or basically attacked from any other external components. So that's the KMS that started. The KMS needs to start first. Then we start the dealers. And once, so what we'll do is we'll start this SGX components, then we'll go back and start the data plane and configure the MME and the HSS. And I'll come back to this particular screen and talk more about the SGX stuff. All right, so dealer in has started. It's waiting for connection from the DP, which is good. We start the dealer out. Again, it's going to start, connect to the KMS, get its keys. And once that happens, it's ready to accept connection from the CTF. Here, we'll start the CTF. We'll start the CDF. So everything is running here. You can look at the router screen. The router screen is showing some of the messages that have been transferred through the router previously during our previous tests. So now we go back to our main screen, which is the load tester with CP and DP. So here we start the DP first. So the DP starts. We also have the KNI configuration scripts running in parallel. So once the DP starts, the KNI interfaces would be configured. So here you go. The KNI interfaces are configured. The DP is ready. So we'll go back to the CP screen and we'll start the CP. All right, so the CP is starting. Again, if you look at the DP screen here, you can see the DP actually got connected to the SGX dealers, and they exchanged a lot of information. They basically challenged each other and to make sure that they can trust each other. And only after they established the trust session, they established a channel. Now they have a fully secure end-to-end SSL channel through which the charge data records would be sent. All right, so go back to our last screen, which is the HSS MME screen. Here we go and let's start the HSS first. There you go, the HSS starts. Then we go and start the MME. The MME starts. And then we come back and start the S1A interface handlers. Then S11 handler, and finally we start the S6A handler, basically which talks to the HSS. So at this point it's ready basically to accept signaling transactions. So the setup is ready. Now we'll go to our load tester and run the test basically. So the test here is basically, for the sake of this demo, we have reduced the number of UEs. We have reduced the number of transactions per second as well. So right now, if you look carefully, it's actually doing a attach. That means the create session, modified sessions messages are being sent at a rate of 250 messages per second, and it will configure up to 20,000 UEs. And you can see the control plane being pumped with that signaling transactions. And also, if you take a look at here on the MME screen and the HSS screen, you can see all the transactions being logged here. And here on the top right corner, you can see the number of UEs that have been created so far. If you quickly go and look at this screen, which is the SGX screen, you can see a new stream has been created for this new test, and it was sent to the router, and our SGX dealer is now accepted that stream. So when we go back here, so at this point the attach sequence is completed, and the traffic generator is now ready to pump the data traffic to the DP. So there's one new interface and the SGI interface of the DP. They are being pumped with data traffic by the traffic generator. So do we see any traffic? Unfortunately, no, but that's okay. We have, so I'll quickly take you through the sequence, what would have happened here. If you can check, if you're looking at my screen, so here the data traffic as it was getting pumped by traffic generator. The DP would have received the uplink and downlink traffic.
You're actually seeing the traffic. Go to the DP console. You have the DP traffic.
Oh, there is? Okay.
Yeah, please go to the DP console. Bottom right. No, not this one. I saw a DP traffic console.
Yeah, there's a DP traffic console.
No, there's one more.
That's fine.
KNI scripts?
They're all configured. They're configured as part of the script itself. So it's okay. So we have the demo, the video capture, so the same. So basically, here if you look at that, I'll quickly show you this. So after the traffic, the 30-second traffic is pumped through the test generator. The test generator starts the detached sequence, again at the same rate, 250 per second. And once that's done, you can see the MME screen where the detached sequence starts, and it's getting the delete session requests, and that keeps going. While that is happening, you can you see the traffic on the CDR side, the charge data record side, where the SGX dealers are handling the charge data record securely. There you can see the messages flowing through the SGX routing system. And what happens is, as it's getting the records generated by the DP, it's actually as it's getting the records from the DP, they're actually stored by the dealer route. They're stored in a secure file, again protected by SGX. So here we are waiting for the entire detached sequence to be completed. Once that is completed, then we basically wait for the file close command or the stream close command that comes from the DP. And once the DP sends the file close command, the SGX dealer is going to close the file and say, okay, I'm done with this file. On the next request, I'll create a new file. And it moves that file into a folder where the CTF and CDF components are basically waiting for a new file that they can process. Okay, so here we see the generator screen. It has completed the sequence. For now, for the demo, at least for the video, we configured for 32,000 UVs. For the live demo, we configured for 20,000. But here, that's the verdict that has come out from the generator. And then we go here to the MME screen. We see the statistics here, 32,000 attached, then 32,000 detached. And we continue with our SGX screen, which will basically show you the CTF and CDF being kicked off because the SGX system has produced a new secure file, and the CTF and CDF, they are going to talk to the SGX system again, go through the entire trust relationship procedure to make sure that the system and the communication is trusted, and then the SGX system delivers all those messages to the CTF. Okay, so with that, I think that was a quick demo. Sorry about the glitch. There were some issues, but luckily we had the video captured last night. So yeah, with that, I'm done. Anything else?
We go to CI/CD.
Yeah, we move to CI/CD. Thank you.
Sandeep?
Sandeep or Mikhail is going to share.
Mikhail?
Mikhail or Sandeep, yeah. Do you have...
Okay, I'm not seeing the screen yet. Okay, this is Mikhail speaking. Hello, everyone. Just a very few words on the CI/CD flow where we are working on. This is basically, let's say, a standard CI/CD process. There are different actors involved and different actions involved. So basically, the idea is that developers, they can submit patches on the different repositories that have been provided to the community. Then these patches will be evaluated by reviewers that will be appointed and will be scored with +1, +2 voting according to the rules that the TST group will decide for this project. And if the patch is accepted by reviewers, it will move on into the flow and will trigger Jenkins job that will basically run on a cluster that is available as a backend infrastructure to this CI/CD flow. End-to-end tests on the system. If these tests will pass, then the patch will be accepted and put into the project. So, as I said, there are several roles. There is the role of the developers and from the community. There is a role which involves mainly us in the definition of which Jenkins jobs to define for this flow, pass-fail criteria, which traffic tests to run or not to run in the different configurations. And there is the role of people actually writing the actual Jenkins file for these jobs. Basically, the process is ongoing. There is still a lot of work to be done, but the status is okay. This infrastructure is available, so the backend is there. All the pieces are connected together, and you are able to do basic provisioning and test of control plane and run plane in an automatic build triggered from a Jenkins job. This is my basically flash on the CI/CD process. I'm sure we will come into more details, but for now, this is my contribution.
Right, thank you.
Thank you, Mikhail. So I think we can open it up, Christian, now for now Q&A. There have been posts. So Sandeep, Kaushik, if you guys have captured, you can. Some of the posts from Muran I answered, and then I would like to give Oz about 5 minutes to see what are the interest areas, where do we want to dig deep. This is a series, so yeah. So we want to, any questions that we want to field right now? Okay, Oz, you want to take the floor and wrap up? Oz and Christian.
Yes, sure. Thank you, all presenters, for the workshop. At this stage, I also want to make people aware that there is a project at ONF that we just announced yesterday, along with OMEC, which is COMAC. It stands for Converged Multi-Access and Core. And COMAC will be consuming OMEC. It is a project within ONF that will develop a reference design and a corresponding exemplar platform. And the goal of COMAC in general is to develop a modular, cost-efficient system and components with well-defined interfaces to enable access and core networks towards 5G. So in that light, COMAC is going to develop a streamlined, simple, and cost-efficient implementation of the 3GPP cellular core, which is effectively what OMEC will be doing. And then, but in addition to that, COMAC will also work on a converged user plane function that unifies the user plane components of fixed broadband, 3GPP cellular core, and the virtualized 3GPP cellular radio access. That would all naturally be hosted at the multi-access edge cloud. And it will also develop a suite of control plane functions and applications that would intelligently be engaged to ensure proper and standards compliant and programmatic control of that user plane. After that announcement, I also want to invite everyone who is attending MWC to come see the ONF booth. At the ONF booth, we will be showcasing a demo where we will be running the OMEC code in a distributed fashion, where the user plane is going to be residing at the core-based multi-access edge in Barcelona, and all the control plane containers are going to be running in Deutsche Telekom premises outside Spain. And in parallel, the multi-access edge is going to also be our sort of pre-COMAC demo, where we are going to showcase broadband access and cellular access melts under a single edge cloud with a unified Kubernetes and and SDN control, ONOS, and the corresponding services control overseeing both access. So do come see it. It'll be a great demo, and you'll get to see also OMEC in action with real commercially available small cells. Thank you.
Christian, any wrap-ups?
Again, thank you. We will be putting this slide on the wiki, and some people at some conference we'll remove the Intel confidential on the slide. This was just a template, default template we used here.
I have a question on the OMEC itself. At ONF, do you have a setup at ONF where somebody can sort of log in and see how OMEC is running?
So, Bud, the setup is hosted at Intel Labs, and Polaris has access to Intel Labs. So you guys can absolutely log in and see how OMEC is running.
Yeah, his question was you mean OMEC at MWC, Bud?
No, I was thinking at ONF lab itself.
Okay.
Should we not have a setup at ONF lab itself other than Intel?
I'll let Oz answer that. It's more about data center space, power, etc.
Yeah, exactly. So that is going to be a decision that the TST will have to make. Point taken. Again, this being now an open source project, I don't want to presume anything. We will, as the TST members decide, we'll take action accordingly.
Okay, all right. And also from Polaris perspective, during the MWC, if you need any help in any way for the demo or anything, please let us know. We have our own booth and our people would be there. So anything you need, we should be able to extend that help there at MWC.
Thank you, Bud. Well appreciated. And at the very least, though, please do come see us.
Okay, we certainly would. Thank you.
All right, I'll just take 1 more minute here. I just want to show you the demo, the live demo that we're trying. There was a glitch in the configuration. The data plane traffic is flowing fine. We can see on the data plane right-hand side panel. Am I not sharing?
Okay. No, you want to share from that?
I thought I was sharing. Okay, let me see.
Thank you, Somnath. We didn't want the community to think we are pulling a hoodie.
No, this is just a configuration. So here, there you go. And so full traffic flowing through data plane, uplink, downlink.
Somnath, you want to say what did he change? So that way people know. At least.
Okay, that was the sequence. Okay, the sequence in which the S1 interface, S1 and S6A interface were started. That was reversed. So obviously it was live demo, so I missed the sequence. I fixed that. So now that has been fixed. So now we run the test again, and all the data flow, uplink and downlink, going smooth now. Going back to the screen for the HSS and the MME, you can see 20,000 UV attached, 20,000 UV detached, has gone through the full procedure here. And finally, we look at the SGX screens, and all the records have been transferred correctly.
Somnath, I want to take a minute and tease 58 people who are on the call.
Sure. Go ahead.
And thank you for coming back and saying, yes, you fixed it. But more importantly, the question I have for this community is, guys, my colleague and partner in crime basically said there's a sequence mismatch. So the question Somnath, you want to keep your screen? The question I have for each one of you is, why does sequence matter? What's the big diff if we started HSS after we started the S Gateway C or the MME? Think about it. You guys can answer now, you can come back later, and that basically sets us up for where do you want to deep dive. So there are issues which are essentially usage issues. What Somnath just pointed out is when you deploy, there's a sequencing of operations, which I'm pretty sure network op guys understand. what Somnath went through is a sequencing of NetOps, network operations. This wouldn't happen on a network, but I would like you guys to think what we just saw here is provisioning of flows, initialization of states of 6 different VNFs that need to come up in a specific sequence. This is not a bug. It's operations kickoff, initialization. There are contributions we can have even here. So I'm going to stop here. The question is to you folks, think about what we just saw. It's fantastic that you hit an issue. It's also fantastic you understand the reason why the issue was hit. More importantly, we would like to know as developers, where do you want to peel this thing apart? We really need your help. We want to rip the covers off of this thing and show you what is working, what really works, and what really does not work. We need your help. Christian?
Awesome. Thank you.
Yeah, no, thank you for the community. And as Ashok and Oz mentioned, this is a community project, right? It has been, initiated by Sprint, Intel, ONF, HCL, but we'd love the community at large to come and contribute, and tell us, what's important, what next feature is important moving forward, right? Then, the TST will decide, we'll rank them by order, and will be implemented, and tested, one by one, right? Ideally, we'd love this to end up, in some field trial, and we know there are a couple of field trials ongoing by, major operators, right? So it would be great to extend this and move this forward with COMAC after, and towards 5G, full 5G deployment.
Yeah, we need your help. Sure.
I have one acknowledgement which we would be remiss without. We have GS Lab members on this call, and the critical mass of this code that we see today, yes, the finishing line is where we took it past the finishing line to OMEC. GS Lab, thank you to the team of GS Lab team here. The critical mass of this code, including the MME and many components of the S and the P gateway, etc. The critical mass where we are able to beat our chest and say we are doing 50,000 flows, etc., is thanks to GS Labs. Thank you, guys.
And including Ashok, including the SGX component.
Yeah.
So we definitely owe it to GS Labs there. Thank you.
Hey, thank you, Ashok. Thank you, Somnath.
Sure.
Okay, thank you, guys.
Thank you.
And we'll be happy to come back for another deep dive if a topic is is of interest.
Yep.
Thanks, guys. Bye-bye. See you.
All right. Thank you.
Bye-bye.
Thank you.
Bye.